Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a super exponential equation with complex numbers. If you're new to complex numbers, go ahead and check out my lecture videos. If you like algebra, number theory, and trigonometry problems, go ahead and check out cyber math, cyber with an S. So we have this equation, z to the power z equals e to the power negative pi over 2. And we're going to solve for z. How do you solve when you're given z to the power z, right? For example, if I gave you z to the power z equals 4, you could probably write the 4 as 2 to the second power, and then just conclude that z equals 2, because z equals 2 would work. Well, at least that would be one of the solutions. But that doesn't guarantee that those are the only solutions. So you kind of need to solve it in a general sense, right? But in this case, we have a really complex case because we don't have a nice number like 4, where it can easily be written as 2 to the second power. So what number to the same power equals this number? That's what we're trying to find, right? So to be able to do that, we're going to go ahead and use natural log and then some other properties, and we're going to use a special type of function, which I know some of you really like, right? Or maybe quite the opposite. So let's go ahead and see what happens. Z to the power z equals e to the power negative pi over 2. Also notice that z is a complex number and z to the power z is a real number. That doesn't mean it's not a complex number, because real numbers are also complex numbers, but we prefer to call them real numbers. To solve it, I could probably replace z with something like r times e to the power I theta, right? Or I could call it z equals a plus bi. These are different representations of a complex numbers. This one doesn't seem very helpful, because what is a plus b to the power a plus b? That's gonna be pretty complicated, even though in one of the videos, I think, we came up with a formula for something like this. And you can look it up. I don't know where it is. I've done quite a few problems. But if somebody can find that problem, that would be really awesome. But I made a video about raising a complex number to another complex power. Of course, in this case, we're looking for the same thing. So it'll probably be slightly easier. But anyways, there's a formula for this, which we came up with in that video. Or we could use this, which might be a little easier because we have a lot of exponents here, right? Or exponentials. The problem, though, this is going to be a little complicated. Well, first of all, you can do the following. Whenever you have something like r times e to the I theta, by the way, this is the polar form, thanks to Euler, that we can write a complex number in. And here r represents the absolute value, or modulus, and theta is the argument or the angle, which we usually call ARG. So when a complex number is plotted, there is an angle, and the distance from 0 is called the modulus. Okay? That's basically what it is. In this case, we might be a little luckier because we're going to be getting some powers from here, which we can set equal to this one, right? But I'm going to do it differently. Maybe we can get back to this if we have time left. I don't know, or if I remember. But let's go ahead and do it this way. We have z to the power z equals e to the power negative pi over 2. Let's go ahead and actually log both sides. Let me move this a little bit so you can see how I log this. And when I log both sides, actually with the natural log, normally people would write log for the complex logarithm, but I like to write ln. So you can kind of write this as z ln z, and then this will just become negative pi over 2. Awesome. That's cool, isn't it? I mean, it looks a little better than the original equation, because at least we don't have superpower like z to the power z, right? Now, here's the challenge. We need to express this in such a way that we can apply a special type of function. Let me tell you a little bit about the function. The function is called Lambert's W function, okay? And W function is basically written as follows. You have a big W that takes t e to the t as an input, and the output is t. Very simple, right? Well, if you think about t to the t, which is kind of like a product, and this is called the product log. Because if you think about the opposite of e to the t, it's ln t, right? That's the logarithm. But this is the product logarithm, and Wolfram Alpha actually recognizes this notation if you use product log, one word, okay? Anyway, so how does this function work? Easy. This is your input, and that's your output, right? The same t we're talking about. But wait a minute, is this in that form? Not really, because let's say this is a t, right? This is not e to the t. Or maybe it's the other way around. Okay, so we can do this. Z ln z equals negative pi over 2. So we're going to use an identity here. What is that? The relationship between z and ln z. Do you remember that? Well, e to the power ln z is equal to z. Great. But how am I going to use it? Just replace z with that. So this gives you e to the ln z multiplied by ln z equals negative pi over 2. And you might still be questioning like, so what, right? Okay, great. Let's switch these around. ln z times e to the power ln z equals negative pi over 2. Now, if I call this t, then I get t to the t, which I can apply Lambert's w on. Great. So if we apply w on both sides, which we can definitely do, right? Because w is a well-defined function, even though we don't know we know how it's defined, but we don't have an explicit formula for that. You can w both sides. In other words, if t1 equals t2, then w of t1 is equal to w of t2. This is just the well-definedness of functions, or whatever it's called, okay? After this, we get this. So basically, what's going to happen is here we're going to be getting t as an input. T as an output. And if you remember, we input this and we output that, right? So in this case, our output is going to be ln z. So we're almost there, right? We're so close to z because remember, our goal was to solve for z. So again, we're going to use the same identity. Z is e to the power ln z. So z is going to be e to the power ln z, which is w of negative pi over 2. You could probably leave it like that, and you should probably get some points. This is on a test, but again, check with your professor. But what exactly is this, right? Is there a better way to write it? Maybe. Let's find out. So notice that we were able to, before we w'd both sides, we were able to write the left-hand side in the form of t to the t. Can we do something to the right-hand side as well? This is what I'm trying to say. If you have t to the t equals negative pi over 2, can I write this as c e to the c, so I can just apply w on both sides and conclude that t is equal to c? At least that would be one of the solutions, right? And let's try that. So how do you write negative pi over 2 as c e to the c? That wouldn't be very easy to solve. But we can do something about it. We got to remember a couple different things here. One of them is pi over 2 is the argument for I. So if you consider the polar representation of I, which will be right here, its argument, at least the principal argument, would be pi over 2. In other words, I can be written as e to the power I pi over 2. Again, for the principal representation, like the principal value, right? Okay, how does that relate to pi over 2? So here's what we're going to do. We're going to think about the logarithm of this number. So what is the natural log of I? Well, let's log both sides. And ln I is I pi over 2. Great. And again, how does that help, right? So here's where we are. Let me go back and show you what we have. ln z times e to the ln z equals negative pi over 2. That's where we are, right? Okay, great. Now, how can I use this information? right, to get to this? Well, if you compare those two things and take a good look, you're hopefully going to realize that negative pi over 2 can be written as negative 1 times pi over 2. Duh, I mean, it's obvious. But not only that, but also negative 1 is I squared. Beautiful, right? Well, I forgot to say that at the beginning. Sorry about that. Usually when I define a complex number, which I didn't do this time, I talk about I. But I is the square root of negative 1. Let's just do a little bit of notes here. So I squared will be negative 1 all the time. Yes, there are two square roots for each complex number except for 0. But in the case of negative 1, I is considered the principal square root. That's what we're talking about. But I squared is always, 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 always negative 1. Okay? So that doesn't change. So we can replace negative 1 with I squared. That's good, right? But how does that help? One more time, you might be questioning again, right? If it's not super clear. Well, let's go ahead and find out. I'm going to replace negative pi over 2 with I squared times pi over 2. And then do the golden split. How? I'm going to write this as I times I pi over 2, because I times I is I squared, obviously, right? And then, this is going to give me something super duper nice. Guess what? This is ln I is equal to this. So this is ln I. Nice, right? So this is ln I. Now I can write it as follows. ln z times e to the ln z. Okay, I don't have an e here, but we can do that. How? We know that I is e to the power ln I. So let's replace I with that. E to the power ln I multiplied by ln I. ln z times e to the power ln z. At this point, you probably know the solution, but let's do this for, completeness sake. I'm going to switch these around because I want to have the e to the something last. And if you remember, our structure was like this, right? T to the t. So now here's the thing. If you w both sides, then you're going to arrive at the solution real quick. Well, this wasn't a quick video, but I wanted to explain everything in great detail. Hopefully you don't mind. Some people do. But anyways, if you w both sides, you're going to end up with t, right? And this is c. So ln z is going to equal ln I. Now here's a $1 million question. Does this necessarily imply that z is equal to I, or is there something else about it, right? Because when you log a complex number, you kind of have to think about it this way. You have to ln the absolute value. By the way, they usually write this as log, just letting you know so you're not surprised, because that's a complex logarithm. But this is a real valued logarithm because z is supposed to be, or the absolute value of z is supposed to be greater than 0. And z cannot be 0 here, so the 0 doesn't have an ln, even in the complex world. But this gives us I times the argument of z. So in the case of ln, we have this thing, right? ln over z, but then we don't have the I times part. So you could probably add something to this, right? At least write this as maybe plus ln e to the power I pi. No, it's not going to work. Anyways, hopefully you can figure it out. I couldn't. But anyways, this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cyber Math and aplusbi. And bye-bye.